Hai semua, Assalamualaikum. Okay, so hari ni Coach akan continue topik sequence and series. Okay, so dia punya subtopik ialah sequence for today. Okay, sekejap Coach saya share screen sekejap. Okay, so before this we learn about arithmetic and arithmetic progressions. Okay, arithmetic progressions ni dia is about addition. Okay, so dia punya keyword kat sini ialah firstly keyword here is sini. Okay, so here the keyword again, first term, okay, is 1. Okay, and then common difference. Okay, dekat arithmetic progressions ni it is addition of the common difference. Okay, so kita tengok this example 6.5 ni. Okay, so here so this one okay, given the first term is 1, common difference is 3. Okay, so we start with 1. Okay, and then we add 3. Okay, because common difference is 3, so we will get 4, and then again plus 3 we will get 7. Okay, and then for the next term, okay, next sebutan is again plus 3, we will get 10 for the next sequence. Okay, that's why last here this is the sequence. Okay, 1, 4, 7, 10, and so on. Okay, so this is the first term, second term, third term, fourth term, and so on. Okay, so now today we are going to learn about geometric progressions. Okay, so this one, okay, geometric progressions. Okay, sekejap saya buka saya punya note sekejap. Okay, so geometric progression ni, okay, is a sequence where each term is found by multiplying the previous term, okay, by a fixed quantity called common ratio. Okay, so keyword here dekat sini, okay, we have to multiply with the common ratio. Okay, okay, so we see for example 6.7. Okay, this one. Okay, so the answer is, and the question is, write down the geometric progression whose first term is 1. Okay, and then the common ratio is 1/2. Okay, so we just highlight the main keyword here. Okay, so the keyword here is first term is given 1. Okay, common ratio is 1/2. Okay, so we just write down 1 first, 1. And then multiply. Okay, remember geometry is about multiplication. 1/2. Okay, and then we will get 1/2. Okay, and then for the next term, we multiply with 1/2, and then we will get 1/4. Okay, do the repeated process. So this one we will get 1/8. Okay, so that's how we get this sequence. Okay, 1/1, 1/2, 1/4, and 1/8. Okay, next. Okay, so this one. Okay, generally geometric progression, we can write in this form. Okay, so A is the first term, and then common ratio R. Okay, and before this arithmetic progressions, we call it common difference, so it is D. Okay, so this one we can also write in recursively. Okay, recursively, so we just write down. Okay, so this is the AR2 again, but we have again A as the first term, R is the common ratio, and then we have K term. Okay, so here we can write it as AR K minus 1. Okay, so that's why in here we get A. Okay, so because let's say K is 1. Okay, so AR 1 minus 1. So you will have AR 0, which is equal to 1. So you just write down A. Okay. Okay, and then okay. Okay, so now now we are going to enter about limit. Okay, we are going to learn about limit. Okay, so this is the example. Okay, in the first case. Okay, so let's say this is the first case. We have s of k equal to 2, 4, 6, 8. Okay, this is the sequence, infinite sequence. Okay, because it has dot 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 at the end, so infinite sequence. Okay, so in case 1, we can say that as the sequence increase, so it goes without bound. Okay, let's say here you can see it will be continue. Let's say 10, it keep increasing until infinity. So this sequence we call it unbounded. Okay, okay, so for in case 2, okay, s of k is equal to 1, 1 over 2, 1 over 4, and dot dot dot, because it is infinite again. Okay, so in case 2, okay, successive terms get smaller and smaller. Okay, why? As you can see here, 1 over 2, 1 over 4, and then 1 over 8, and then 1 over, sorry, and then let's say 1 over, let's say simply we can say 110, it can go until 100. So this is 0.1, this is 0.01. So it keep getting smaller, okay, until the end. So it will getting closer to 0. Okay, so here it says that as k, okay, goes to infinity, okay, the function lastly will be equal to 0. Okay, the value will be equal to 0. Okay, so this is where the concept of limit comes. Okay, so here in case 2, the limit, okay, of this function is equal to 0. Okay, so how to write it is we just write this. So we just write, okay, limit shorten to lim, and then k to infinity, and then the function s of k. Okay, so it will be equal to 0. Okay, or in other case, okay, okay, in other case it can be a certain number. The limit can be come into a certain number. Okay, so here, okay, the sequence converge to a limit L. Okay, which means the answer or will be either close to L. Okay, and then okay, this one is still converge. Okay, let's say other values such as maybe can be 10 or 3 or any integers, any number, okay? And then, okay, whenever the sequence is not convergent, so we call it will be divergent, okay? Okay, and then okay, this is another type of sequence. Okay, as we can see here, the value x of k will be equal to -1, 1, -1, 1, -1. Okay, so it will look like this, okay? Okay, so 1, -1, okay? So it will be look like this, okay? Okay, this is the first term, second term, third term, okay, third term, fourth term, fifth term, okay? So we call this as oscillate. Okay, the sequence is oscillate. Okay. Okay, so and then, okay, actually properties, you can see this in the, we call the wording in the gray box as properties, okay? So we can see here that, so I can see that this is the properties of limit, okay? So, if xk plus minus yk, so the limit also can be plus minus, okay? Let's say this is L1 and then this is L2, so it can be plus minus as well, okay? And then for the second case, we see here that we multiply constant with the function, so the limit also will become, we can multiply with c, okay? And then, okay, so here we multiply, let's say L1, L2, so the limit also become L1, L2. We just multiply the limit. Okay, so when the function is divided with another function, so the same goes to the limit as well, okay? So the limit will be divided by other limit of other function, okay? So, okay, so next, so we will look into the example, okay? So we try to solve for the question here in example 6.8. Okay, so for the first one, so we can see that, okay, so this is the function, okay? So for 1, it will be 1/1, and then 1/2, 1/3, 1/4. Okay, so you can see this one equal to 0.5. This one equal to 0.33, meaning that it will be getting smaller, okay? It will close enough to 0. Okay, so we can say here that the limit, okay, of this function xk, okay, with k to infinity is equal to 0. Okay, and then next one, okay? Okay, so next one, sk is equal to 5. So meaning that there is no k. So whatever, so it maintain the value, it will be 5. Okay, so we can say that the limit, okay, of this function s of k, which is 5, k to infinity will be 5, because it will be maintained whenever variable, it will be 5. Okay, and then next one, okay, so this one, okay, so 3 plus 1/1, okay, and then 3 plus 1 over 2, then 3, 1 over 3. Okay, as we can see, okay, this one, okay, is repeated if the A, okay? Okay, this one. So meaning that this one, okay, plus 1 over 3. This, what we call this fraction will be 10 as the k increase, as the k goes to infinity. This one will be close enough to 0. So what left is 3. Okay, at the end, it will be 3. Okay, it will be 3 plus 0. Okay, so you can say that the limit s of k, okay, when k tend to infinity, we will get 3 at the end. Okay, so this is converge to 3. Okay, and then for this one, so this one, so for this one, 1, let's say 2, 1 over 3. Okay, same. Okay, the process is repeated, so we know this one will be 10 to 0. So again, this limit of s of k tend to infinity. So this one will be 0. Okay, okay, so for case E, okay, so case E, we just, can I write up here? Okay, okay, so x k equal to k squared. Okay, so k is 1, 2, 3, 4, and so on. So we need we will get the sequence as 1, okay, and then 4, okay, and then 9, and then 16, and so on. Okay, as you can see, it will go, it will tend closer to infinity. Okay, so we can say lim, but here we cannot say that the limit is equal to infinity. Okay, so we have a look at the answer. So here E, which is the last one, so increase the sequence will be increasing without bound, okay, which is infinity. Okay, so it has no limit, it is divergent. Okay, so here it has no limit. Okay, or else you can say it is divergent. Okay, and then for okay, so next, okay, so this is example 6.9. Okay, so we read the question. Given a sequence with general term as of k, so this is in term of fraction. Okay, so here we have to find the limit, okay, as k goes to infinity. Okay, so in this case, what we have to do is, okay, so first we have to let, okay, so I just write down again as k equal to k minus 1, k plus 1. Okay, so first we have to let k equal to infinity. So we must make sure that at the end, okay, the aim is to make into this form, okay, to make into this form 1 over infinity, or we can say 1 over k. Okay, so here, okay, so this is the numerator, okay, and this is the denominator. So we have to do one by one. Okay, so again, the key here is the term is k. Okay, the function has k. Okay, so for numerator, okay, k minus 1. Okay, divide by k. Okay, the highest k, the highest k. Okay, I mean, let's say if k squared, so we have to to divide with k squared. Okay, next example I will show you. Okay, so and then for denominator, so k plus k plus 1 minus over k as well. Okay, so this one, so simplify, so we have 1 minus 1 k. Okay, and then this one, k over k plus 1 over k. So we have 1 plus 1 over k. Okay, so we convert k into infinity. Okay, so 1 over infinity, then 1 plus 1 over infinity. Okay, so this is will be 0. Okay, this one 0. So what left is 1. Okay, so left is 1. So numerator and denominator is equal to 1. So will be 1 over 1. So the limit is 1. Okay, so is it correct? Okay, so this is, okay, so we get the same, right? Okay, 1. So the limit k, sorry, okay, the function, okay, s of k, when k tend to go to infinity, it will be 1. Okay, so you can here you can write at the simplification of function, or you can also write the full function. It's up to you. Okay, both is correct. Okay, the way of writing the limits. Okay, and then so we see for example 6.10. Okay, so this is again in terms of fraction, we have numerator. Okay, we have numerator and we have the denominator. Okay, so you do it beside this one. Okay, so the function is s of k equal to 3k squared minus 5k plus 6 over k squared plus 2k plus 1. Okay, so again, this is the numerator, this is the denominator. Okay, numerator, this is denominator. Okay, okay, so we have to let k equal to infinity. Okay, so the key here is, what is the highest form of k? So we can see is k squared. There is no other highest form of k except for k squared. There is no k to the power of 3. Okay, so what we have to do is we have to divide the numerator with k squared. Okay, same goes to the denominator. Okay, numerator. Okay, so we do the numerator first. So 3k squared minus 5k plus 6. Okay, divided with k squared. So we can write one by one. So 3k squared divide k squared minus 5k over k squared plus 6 over k squared. So this one we will get 3, this one 5 over k, and then plus 6 over k squared. Okay, so convert k into infinity. Okay, 6 infinity. So this one we will get 0. This one also 0. So what left is 3. Okay, now we do for the denominator. Okay, denominator. So k squared plus 2k plus 1 divide with k squared. Okay, simplify, break into 1 by 1. K squared divided by k squared. So this is will be 1 plus 2 over k and plus 1 over k squared. Okay, convert into the k into infinity. For infinity. So this one will be 0, this one will be 0. So what left is 1. Okay, so write down again. Numerator we have 3 over 1. So it will be 3. So the limit of this function, okay, s of k, when k goes to infinity, we will have equal to 3. The limit is 3. Okay. This one. So the limit is 3. Okay. Same goes for this one. Okay. Okay, so that's it for. Okay, so maybe we can do the last one, which is, I think no need. Okay, so that's it for sequence. Okay, so next we will continue with series.